Okay, as you can see in today's video, we're going to go over nuclear fusion and mass defect and binding energy when we combine a hydrogen 2, which is known as a deuterium, and a hydrogen 3 atom, which is known as a tritium. And when we do that, we're going to get a helium 4 and a neutron. And this is nuclear fusion, and this is what occurs in the sun. This is where the sun gets its energy from the combination, for example, of deuterium and tritium are combined, and they're going to form a helium nucleus, and they're going to release energy and a neutron. And we are going to use the average atomic masses of those things to determine the energy that is released from that reaction. So here's the reaction again. We have hydrogen 2, hydrogen 3, deuterium and tritium. We react those two together. We can combine those two in nuclear fusion. And when we do that, we get helium 4 and a neutron. Now this basically just becomes a problem involving conservation of mass. We're going to look up in the internet somewhere, it's given to you the mass of the hydrogen 2, the mass of the hydrogen 3 on the left hand side, and then the helium and then the neutron on the right hand side. It's going to be conservation of mass. There's going to be a difference in mass. The difference in mass, the mass defect, we're going to convert the mass defect into binding energy. All right, or just energy, but called binding energy. So hydrogen 2 has a mass of 2.014101, and this is U in atomic mass units. We're going to do this using the atomic mass units. Hydrogen 3, tritium, is 3.016049. Helium is 4002602, and the mass of a neutron, the rest mass of a neutron, is 1.008664 atomic mass units. Again, this is all atomic mass units. Now, as I said, this is just conservation mass. These are the constituents that we have on the left-hand side. These are the constituents we have on the right-hand side. We're just going to add them up. So we add up what we have on the left-hand side, and we get that 5030150. And on the right-hand side, we're going to get 5011. And you'll notice the mass on the right-hand side, the mass of the products is less than the mass of the reactants for this nuclear fusion reaction, and that's our binding energy. So we're just going to find the difference of those two, and the difference of those two, which we call the mass defect. That's the mass defect is 0.018884 atomic mass units. And we're going to do it two different ways. We're going to start off by using Einstein's equation equals mc squared to convert this mass, this is the mass in the equation, into energy. Now the energy is given in joules when we use this equation. The mass has to be in kilograms, and we have atomic mass units, and then we're going to multiply that by c squared, which c is the speed of light squared in this case. So in order to use this equation, we first have to convert our atomic mass units into kilograms, which we can do that very simply by taking our atomic mass units. This is our atomic mass units. This is a mass defect. We're going to convert that because we know that these are all just constants. This is all just unit conversion. One atomic mass unit is 1.66 times 10 to the minus 27 kilograms. That gives us 3.13 times 10 to the minus 29 kilograms. Okay, this is our mass defect in atomic mass units. This is the equivalent amount of mass in kilograms. So it's the same thing. We're just converting from one unit of mass to another unit of mass. And then you can see we can just plug that into our equation here, 3.13 10 to the minus 29 kilograms, multiply that by the speed of light squared, and we get that the mass defect converted into energy in joules is 2.82 times 10 to the minus 12 joules. Okay, now usually that's the binding energy, but usually when we have binding energy, we give the binding energy in electron volts or mega electron volts. So we're just going to convert that unit of energy, joules, into a different unit of energy, which is electron volts. And we know that 1 electron volt is 1.6 times 10 to the minus 19 joules, an electron and a volt. And that gives us that is 17.6 times 10 to the 6 electron volts, which is 17.6 mega electron volts, because mega is times 10 to the 6th. Okay, so this is the mass defect in atomic mass units. This is the mass defect in kilograms. This is the binding energy in joules, which we used Einstein's equation to convert, and then this is the binding energy in the typical units that it's expressed in, which is mega electron volts. Now there is a little simpler way to do that, because there's a direct conversion, you call it a direct conversion between atomic mass units and mega electron volts. So we're going to just convert our atomic mass units once again using the fact that we know this time that 1 atomic mass unit is equal to 931.5 mega electron volts. You remember in the previous slide we went from atomic mass units to kilograms, and then kilograms to joules, and joules to mega electron volts. We can go right from atomic mass units to mega electron volts because we know that 1 atomic mass units is this many mega electron volts, and we get the same answer, 17.6 mega electron volts. Okay, I think the other way is a little bit more interesting because you see the relationship between the energy and the mass, and Einstein's equation equals mc squared. Doesn't get much more fun than that. Okay, so there you go. Thank you very much for watching. Hope you found it helpful. If you did, please do all the following 3 things. Subscribe to my channel, get all my excellent physics, chemistry, and math videos. Give me a thumbs up for this video, and of course, leave me a nice positive comment in the comment section below. Thank you very much for watching. We'll see you in the next video.